All right. Boom. All right. So Friday we talked about how A creates an outward directed field, B also creates an outward directed field. Okay, and they're overlapping at point X. The reality is they're creating their own electric fields at different locations. So you've got like um, A is creating this blue field all over the place. The B is creating its own field all over the place. They're overlapping. To find the total electric field, though, we're going to do head to tail and find the resultant of these. And that's what these red arrows are doing after doing head to tail. And then what we do is connect all these arrows together and create these patterns called electric field lines, which they always go out of positive, as seen here, and go into negative, which we'll be seeing in a little bit. The closer the electric field lines are together, that means the stronger the electric field is. Here it's weak, here it's strong. And the way you figure out which way the direction of the electric field is at a certain location is you look at a path that's tangent to the electric field line. So this would be going that way at that location. Another way to look at it is like if you were to let go of the tennis ball right at this location, which way would it fly? Path tangent to. That would be the direction of the total electric field at that location. So tell your neighbor.
Well, it doesn't even make sense. It's just like, surely. I don't know, but none of the other answers make sense. I'm sure. Are you? Yeah. I'm sure. Sure. I know. I mean, I don't think it's no. I'll say like whoever wins. You know, like.
Correct answer is E. Everybody good with E. They're canceling each other out. That's their electric field lines are spread out right there. Okay. Next question. Right there. Whoop. There's nothing there. It's just a space holder. Like in this location. Okay, let's try this. In the future, try to think of it yourself. Go ahead and talk to your neighbor if you were playing along.
Then maybe it goes to the right. Like going to the next. I don't know. That's a good. Why is there no diagonals? Because in my mind it's diagonal. In my mind it's diagonal. But it's not. But like two diagonals. My mind is wrong. Ow.
Okay. Tell me. No, don't tell me. Show me with your finger which direction the electric field is pointing at this location from this guy. It is going outward, sunshine. Oh, Did I give a little hint there?
No. You did not. You did not. I said.
What? Show me the direction of the electric field from this one at this location. Inward. The total of the resultant of those two vectors. You cut and paste head to tail. Start at the origin. Correct answer is C. To the right. Does that make sense? Okay. Thumbs up if the blue makes sense. Outward directed sun rays going out from the blue. Sunshine. It happens at this location. Sunshine's going that way, radially outward. Okay. The green is going radially inward because it's negatively charged. Okay. At this location, that means at this location it's going inward. Okay. To find the total or resultant of these two vectors, we do head to tail, cut and paste, start at the origin where we started, and draw it to the final head. Okay, good at that. Boom. Talk to your neighbor. Correct answer is, we got a D, B, bubbly biscuits. I like it. That's good. Bubbly biscuits. Okay. It's going out of positive into negative. And then you know that 2 has a greater charge because there's more lines. The electric field lines are more densely packed, creating a stronger electric field than in over here. Okay. Well, we're not going to. All right. There you go. Oh, buddy. A lot going on there. Have a conversation.
Wait, let me think about it. Oh, okay, but one of the things with the Greek is like
It's like supersets.
it's just one line, but like how close the rounds are. But like some of them who cares?
Correct answer is. Correct answer is A. Appreciative apples. All right. Why the electric field lines are more densely packed here? They're closer together. 3, 2, they're a little bit more spread out, and 1, they're obviously more spread out. So 3, 2, 1. Okay. This is a good question. Tell your neighbor and tell them why.
But to be honest, I don't know. I just those
Correct answer is. Got some C's on the table. Got some A's on an A on the table. Some A's. Okay, here we go. So what's going on between this guy and this guy? Attraction or repulsion? Attraction, because it's negatively charged. Okay, so it is attracting. What's going on between these two? Repulsion. Show me with your finger which way it's going to be repelled. Okay, finding the resultant or the total. Do head to tail, and it is going this way.
So why does the question no? Why doesn't the question just say one is negative? Like I don't understand the question. I didn't realize that one was like negative. But that's what that meant. Like why can't it just be like if one is negative, then what direction is it?
So point 1 is just talking about a space, a place in space.
Yeah, I got that.
And then it's saying we put a negatively charged peanut at point 1 is what that's saying. Which way is the peanut? The test charge, the scout is small. Which way is that going to be placed or forced? Okay. All right. So here's another, like we did it one way. I'm going to teach you a different way. This is what you're going to write down. Okay. If you're a note taking person. A positively charged object will be forced in the same direction as electric field. A negatively charged object will be forced in the opposite direction of an electric field. Okay, what do I mean by that? Let's pretend we had a positively charged object right here. Which way would that be forced? Based upon the electric field. Electric field's going this way. If we let go of a tennis ball right at that location, which way would it go? Go this way. So the direction of the electric force on a positively charged object would be in the same direction as the electric field. If it was negatively charged, it would be in the opposite direction of the electric field. All right with that? So up if it was negatively charged. Good? Tell your neighbor. Correct answer is electric field lines go out of positive into negative. Correct answer is B. JP. Great question. They would attract each other, but so a capacitor, they're actually held apart to create an electric field. If you ever heard of a capacitor, like it's an electronic component, it's designed to create an electric field in between them. But yes, they are being attracted, but they're held that way. Okay? So if we were to stick an electron in a capacitor, which way would it be forced? Correct answer is, tell your neighbor and tell them why.
I know how it doesn't know what it's supposed to do. Because if you do like the arrows, the light bulbs. Honestly, it's not just easy. I think it's either I don't know. Or maybe it's not.
Correct answer is? Correct answer is A. Here's two different reasons why A is correct. Electric field lines go out of positive into negative. This is positively charged attracting an electron. This is negatively charged repelling an electron. Both are being forced up. Okay. The other way you can look at it is because it's negatively charged, it's going to be forced in the opposite direction the electric field lines are going. Up. It's a negatively charged. It's an electron. Give that one a shot. Tell your neighbor. Is everybody good with C? Positively charged is being forced in the same direction as the electric field because it's positively charged. Last question. Tell your neighbor.
I really want to say acceleration. It probably just, I was gonna say maybe it's just
It experiences a constant force. It's unbalanced, therefore it will experience acceleration. Okay, constant acceleration. All right, pre-quiz due tomorrow at 7:30. Oh no, it's you. No, we still got some demos. All right, we got. Well, we're doing stuff. Oh. All right. So, first demonstration. Tell me why this happened. Okay, why did that happen? Talk to your neighbors. So are these conductors or insulators? Conductors. What's the charge on the Van de Graaff generator? Negative. So these become negatively charged by conduction, touching. So electrons like each other. Negatively charged objects like each other. No. So they repel. Why do they go off one at a time? Is yes. Which one's heavier? Two of them or one of them? One of them. Not enough to lift two of them up. It's just enough to lift off one at a time. Good to that? Okay. All right. Need a volunteer to stand up here and also be on camera. This will not hurt. What you will do is you will stand up here, put this aluminum rod on your shoe, hang on to this. You will not get hurt so long as you hang on to this until the end of the demonstration. After the end of the demonstration, take this aluminum rod and touch the plumbing. Okay, it will not hurt. Just feel weird. Bailey, come on up. Just on the insulation.
And then you want me to put it on my plate?
Yep, right, like that. Okay.
Oh, I see myself. Bye,
Yeah.
guys.
Okay. You see a little, look at her hair. You see her hair? Like, whoop. See that? guys see her hair? Okay, go ahead. Watch her hair as she touches the plumbing. Go ahead and touch anything silver up here. Does that hurt?
No.
No. What did it feel like? Did you feel anything? Weird. Weird is the operative word. All right, go ahead. You're good. Hop on down. Well done. Well done. Yeah. You didn't see it, and they can like. Yeah. Okay. Yeah. Okay. What happened when these are charged? What happened when these are charged? Spread apart. Why? Yep, they repel each other. Does that make sense? Why Bailey's head or hair stood up? They're just trying to get away from each other. That make sense? Okay. Another volunteer. Come on, it's gonna be cool. Oh, kids. Isaiah. Same thing.
Okay.
Okay. You can watch his hair, but I want you to check out something. Um, yeah, it's gonna be good right there. All right. So listen as he brings after I charge him up. Listen as he brings the rod next to the plumbing. Do anything? Go like that. Shake. A little more aggressive. Okay, you see it? Okay, listen as he brings the rod and watches. Well, yeah. Nice. Okay. What do you think that sound was? No, the. Okay, those were the step leaders. Trying to find like the lightning thing.
Oh yeah.
And then did connection. That makes sense? Okay. All right. Need one more. This one's cool. All right. CJ, come on up. All right.
Can I have metal in my pockets?
Yeah, it's fine. Okay, what I want you to do is hold this rod just out like this. I want you to look at the end of that. This. We're gonna see how dark it gets. People on YouTube probably aren't gonna be able to see this because it's gonna be really dark. Oh. I know. I saw that. I was like, oh, there it is. All right, so we're in the dark.
By touching the thing?
Yeah, you're gonna. Yeah, hold on to that. Don't let go of that. Oh, my computer. Doggone it. Hold on. Doing laps. Oh, I have to shut down everything. That is such a kick in the shorts.
I'm gonna watch the video just like
I don't know if it's still recording. We'll see. All right. Maybe.
Maybe?
Doubtful.
Did you hear that?
All right. Here we go. Ready? Look at the end of the rod. You see it? Oh, I see it barely. You see it? No. Okay. CJ, go ahead and drop. Put the rod down. All right, go ahead and touch the outlet. Saw that one, huh? That was okay.
There was some light, but not a lot.
All right, JP, come on up. Yep. Can you see? No, it doesn't matter. You're not. No one's going to be able to see it. We're going to do this without the rod. So can you see the styrofoam?
I can have metal, yeah.
You'll be fine. Hand on that. Okay, finger out.
Finger out?
Finger. Just point your finger. Okay. You guys might need to step close for this. Don't get too close, but
Why can't we get too close?
you'll find out if you get too close. Just cut. You'll be fine. Come on, like get out of your seat. You're not gonna be able to see this. You gotta come close. Don't get. You'll get. No. CJ, back up. Like that's you give it like a good 4 feet. 4 feet. 4 feet. You will regret it if you're not 4 feet away. Okay, look at the end of his finger. You see it? JP, can you see your finger? Look at the end of your finger. You see it? You see it? Okay, so JP, just hop on down. Here come the lights. Just jump on down.
I guess I keep it all the way.
Sure. Okay, so here's the deal. Did anybody see the purple?
Yes.
Yeah.
Okay, that is known as St. Elmo's fire back in the day. Okay, so what that is a bunch of electrons going out trying to find a better place, and it's ionizing the air around there, causing it to glow purple. Back in the day, during a storm, sometimes the mast on the ship would have that purple coming off the ends of it. And they called that St. Elmo's fire. They thought it was a good omen. Really, it was like the people who saw that and didn't get electrocuted or blown up were like the lucky ones. Like, because usually that means like you're sending off positive streamers, and it's gonna be good times. All right, you're out of here. You got a pre-quiz. We'll later this week.
I thought you wanted to. Put it on the website 30 seconds early.
No big deal.
Just see how well we lose my hair. See how well we can decide whenever we
It's gonna be good. See ya. See ya.